This is the equation that I need to solve. It has two different trigonometric functions, a sine and a cos. I need to transform it to see a single trigonometric function. And in this case, because the right hand side is 0, the first step that I can do is write, I divided here both sides by cos 2x. Cos 2x cannot be 0, because if cos 2x would be 0, sin 2x would be either 1 and minus 1, and this equation will not be fulfilled. So this allows me to divide by cos 2x. I know it is not 0, so I get a single trigonometric function. Tan 2x is negative 3 over 5. Very important at that stage, I will let 2x be y. So my new equation is tan y equals negative 3 over 5. But because x was between 0 and 180 degrees, my y, which is 2x, will be between 0 and 360 degrees. So the domain for y changes. Using my calculator, I can find that y equals, if I input inverse tan and negative 3 over 5, I will find y equals negative 30.96 degrees. Because my domain is in degrees, I need to give my answers in degrees. This is not in the domain, so not applicable. But then the next one, the period of tan is 180 degrees, so I add 180. My next angle is 149.04 degrees. Add another 180, so I get to 39.04 degrees. I can't add another because I'm going out of the domain. Now I divide by 2 and I get my solutions for x. 70.4.52 degrees or 164.52 degrees to 2 decimal places, and these are my answers. When solving a trigonometric equation, the first advice I would give would be to try to get the same trigonometric function. So here we have cotangent y and cosecant y. And generally, I would advise writing everything in terms of sine y and cos y. But in this particular case, it's useful to remember that these two trigonometric functions are linked by a formula, which is on your cover sheet, formula sheet in the additional math exam, and this is a formula. And it will give me easier calculations using this formula. Here we have a quadratic equation. I will let cosec y be t, just to see better what I get. So I get 2t squared plus 3t minus 2 equals 0. So the solutions of these quadratic equations are t1 equals a half and t2 equals minus 2. Let's remember that my equation was an equation in y. So I can go back now and write cosec y equals 1 over 2. Cosec y is, and this is not in your formula booklet, so you need to remember it, 1 over sine y. So sine y equals 2, no solutions. The range of sine is from negative 1 to 1, so no sine can give you 2. Or from the second equation, from the second solution, I get sine y equals negative a half. I like to rely on the trigonometric circle and looking for angles in the first quadrant always. So I'm going to solve the equation sine alpha equals plus a half. And y-axis is a sine axis, so sine equals a half in this point. So with your GDC, with your calculator, alpha is inverse sine of 1 over 2 and gives you 30 degrees. Now I'm looking for the related angles, so angles where sine is negative 1 over 2, and the angles are this one here and this one here. So my y is 180 plus 30, or 360 minus 30. So starting from 0, 180 plus 30, this arc is the same as a 30 degrees arc here. So this is my first solution. And my second solution, start from 0, 360, take away 30. Therefore, my solutions are 210 degrees or 330 degrees. This equation is of another type, and the first thing that I notice is that this time the domain is in radians, so my answers need to be in radians. It's an equation involving a single trigonometric function cos, so I'm going to make cos subject to the formula. This is what we obtain. So I let z plus 1.2 be t to get a simpler equation, but now my equation is cos t equals 2 over 3. However, my t is in this domain, so I'm going to look for solutions in this domain. As always, I'm looking at the trigonometric circle. So within the first revolution, I'm always finding the solutions within the first revolution. And within the first revolution, my t is inverse cos of 2 over 3, which is given by my GDC, by my calculator, 0.841 to 3 significant figures. So this is a cos axis. 2 over 3 is cos of that angle here. So that angle is 0.841 to 3 significant figures. Now, within the first revolution, I have another solution, and my second solution giving me the same cos is here. So my second solution is 2 pi minus 0.841. Now, to move on to the next revolution, the period of cos is 2 pi. So from these two solutions, I'm going to add 2 pi, and then add another 2 pi or subtract 2 pi until I get out of the domain. So I can see, therefore, that the solutions to my equations are t is 0.841. It's not in the domain, so I'm not going to consider it. The next one, which is in the domain, is 2 pi minus 0.841, which is 5.442 to 2 decimal places. Next one is 7.124, 3 decimal places. The next one is already outside the domain, so I'm not going to consider it. Therefore, I have these two solutions. Now remember, z is t minus 1.2, so I'm going to subtract 1.2 from both solutions and get these two solutions to 3 significant figures. Let us take a closer look at the differences between these three equations. In all the cases, we try to reduce the equation to one of the basic trigonometric equations, and I call basic trigonometric equations the equations cos alpha equals a number a, or sine alpha equals a, or tan alpha equals b, c, not necessarily need to be the same letter, so let me choose a b here. But a and b must be between minus 1 and 1 because of the range of sine and cos. C can be any real number. because the range of tan is from minus infinity to plus infinity. So we try to reduce any trigonometric equations to one of the three basic ones. And now please read the comments under A, B, and C to see how we do this in three different ways. Please pause the movie to read this carefully. The difference between the what we call basic equations in cases A and C are that in the case A, your basic trigonometric equation is tan, in case A, is tan 2x equals something. Yeah? So my function y equals tan 2x is obtained from y equals tan x after a horizontal stretch. This is why, in order to make it more clear, I let this 2x be y, and I solve the equation in y, which was the basic ones, but making sure that I change the domain as well for y. In case C, the basic equation is cos z plus 1.2 equals whatever, 2 over 3. So in this case, the basic function y equals cos x is obtained, or this one is obtained from the basic one after a horizontal translation. So I need to make sure that this is reflected in my new domain. So I let z plus 1 over 1.2 equals t, but then I look for a new domain in t. So in all trigonometric equations, the general method is the same. Try to write your equations in terms of a single trigonometric function that can be one of these three, involving maybe some of the horizontal stretch or translation.